Okay. All right. So on behalf of the geotechnical and structural subgroups of the Civil Technical Division of GHIE, I'd like to welcome you all to today's program, this panel discussion on the seismic preparedness of Ghana's cities. You're all welcome here online. Initially, we had planned this to be a hybrid program because it would be very good to meet in person. But nowadays, with our weather and flooding issues, we've decided to make it online for safety of all. All right. Well, in Ghana, we don't face frequent devastations associated with earthquakes, but our history tells us that a seismic event is a reality, it's a possibility in Ghana. Okay, and now with rapid urbanization and increasing infrastructure development, um, and the recent improvements in seismic monitoring by the Ghana Geological Survey Authority, I think there is no better time now to ask ourselves this important question. How prepared are we? How prepared are Ghana's cities for the next significant earthquake? This is something that we really need to discuss. So this evening's discussion will bring together experts from geotechnical engineering, structural engineering, seismology, seismology, and disaster management to share their perspectives on the current state of our preparedness and the steps needed to improve the resilience of our cities and infrastructure. So it is my pleasure to introduce our distinguished panelists today. Um, I would like to give a brief about all of them, but let me mention them first. We have Engineer Professor S.I.K. Ampedu, who is a professor of geotechnical engineering at the Department of Civil Engineering, KNUST. Then we have Mr. Nicholas Opoku, who is a seismologist from the Ghana Geological Survey Authority. Then we have Engineer Beverly Okai. She's a structural engineer with over 20 years experience in structural design, assessment, and rehabilitation of buildings. We also have Engineer Michael Zadok, who is also a structural engineer and specialist in transportation infrastructure and urban roads. And lastly, we have Dr. Mrs. Betha Kusimi. She is the head of geological department at the National Disaster Management Organization, NADMO. So, ladies and gentlemen, these are our panelists for today's discussions. If you would permit me, in fact, I would like to give some background. Engineer Kunedu, what do you think of our panelists so that our audience will know who they are in detail so that they know that we are in good hands this evening.
Is in order, very good order. Please do.
Very, very necessary. Okay. So let me start with Engineer Professor Samuel Ampedu. He's a professor of civil engineering at KNUST with expertise in geotechnical engineering. He's an educator, researcher, and consultant in civil engineering. And as an educator and researcher, he has some 40 years of teaching and research experience at the College of Engineering of KNUST. Yeah, he was the provost of the College of Engineering from 2010 to 2016, during which he helped to shape the direction of engineering education in Ghana. Internationally, too, Prof. Ampedu is known for his expertise in laterites and lateritic soils. This is the material which is predominant in Ghana. He has served as the chair of the International Society of Soil Mechanics and Geotechnical Engineering Technical Committee TC 107 on laterites and lateritic soils. from 2011 to 2019. He was the 43rd president of the GHIE. Yes, so at one point in time, he was our president and the founding member of the Engineering Council of Ghana, during which he helped shape also the practice of engineering in Ghana. So he's shaping not just the education, but also the practice of engineering in Ghana. Currently, he is championing quality assurance, sustainability, and resilience in education, and is playing a key role in the postgraduate education in geotechnical engineering at KNUST. So help me welcome Professor Ampedu with a hi. Everybody just say hi.
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 Thank you.
Hi.
Good. Next, we have Mr. Nicholas Opoku, who is a highly accomplished seismologist and geoscientist with over 20 years of professional experience in earthquake monitoring, seismic hazard assessment, geohazard investigations, and geoscientific research. He currently serves as a deputy director and head of the seismology division at the Ghana Geological Survey Authority, providing strategic leadership to Ghana's national earthquake monitoring and seismic risk management programs. Mr. Opoku has played a pivotal role in the development and modernization of Ghana's seismic monitoring infrastructure, including the installation, operation, and the recent upgrade of the Ghana Digital Seismic Network. I think he was in the news recently when they commissioned this new infrastructure. He holds an MPhil in nuclear earth science from the University of Ghana and a postgraduate diploma in seismology from the International Institute of Seismology and Earthquake Engineering from Japan. If you need to learn anything about earthquakes, there's no other place than Japan, which experiences earthquakes almost every year. So he has a wealth of knowledge to share with us. Mr. Opoku has represented Ghana in several international scientific and technical collaborations with organizations including the Comprehensive Nuclear Test Ban Treaty Organization, the Incorporated Research Institutions for Seismology, German Center for Geosciences, and Africa Array. Now, through his leadership, research, and public engagement efforts, he continues to contribute significantly to strengthening Ghana's resilience against earthquake and geohazard risks, while supporting national initiatives in infrastructure safety, disaster preparedness, and nuclear power development. I remember a few years ago when we met under the ground motion workshop, he was a key resource person discussing the ground motion parameters for design in Ghana. So, ladies and gentlemen, let us welcome Mr. Nicholas Opoku. I don't know if he's joined yet. He's not yet online. Okay, so that is our seismologist. I'm sure he would share a lot of insights with us today. The next panelist is Engineer Michael Zadok, who is a structural engineer with 26 years of post-qualification experience. His expertise spans the analysis and design of building and bridge structures. He also has experience in computer programming through VB.NET programming language. He has a passion for computational structural engineering and the integration of engineering software into the engineering practice. He has MSc DIC concrete structures, BEng civil engineering, and is SPE, senior professional engineer with the Ghana Institution of Engineering. Ladies and gentlemen, Engineer Michael Zadok. Let's say hi to him.
Hi.
Hi.
Thank you.
Hi.
Right. Our next panelist is Engineer Beverly Okai, who is also a structural engineer with over 20 years of professional experience in the design, assessment, and supervision of building projects across West Africa and, of course, Ghana. She holds an MSc in structural engineering from the University of Salford, UK, and MBA in finance from University of Ghana Business School, and a BSc in civil engineering from KNUST. Her experience spans a wide range of projects, including high-rise residential and commercial buildings, healthcare facilities, institutional development, basement structures, and complex residential developments. She has been involved in major projects such as the Agenda 111 healthcare program, infectious disease treatment centers, and multi-story developments for up to 17 stories. She has particular expertise in structural integrity assessments, retrofitting, and rehabilitation of existing structures. So she's bringing a wealth of experience to our discussions today, because one key thing we would want to understand is in our structure, should we start designing structures to resist earthquakes, or we should look at our existing structures and retrofit them against earthquake effects? So she has also served on the GHIE membership interview and exams panel for over 5 years and has undertaken professional training in earthquake engineering, structural repair, retrofitting, and rehabilitation. So her combined experience in the design of new structures and the assessment of existing ones provides valuable insights into our discussions this evening. So ladies and gentlemen, please welcome Engineer Beverly Okai. Let's give her a hi.
Hi, Beverly.
Hello. Thank you. Our last panelist is Dr. Bertha Kusimi. Hope I got your name right, Doc. PhD. She's an emergency preparedness officer with over 15 years of professional experience in disaster risk reduction, emergency preparedness, and urban resilience in Ghana. Over the course of her career, she has worked extensively on hazard assessments, emergency response coordination, community preparedness programs, and capacity building for local authorities and vulnerable communities. Her expertise includes seismic risk awareness, urban disaster planning, incident management, contingency planning, and multi-agency coordination for disaster preparedness and response. She contributed significantly to preparedness planning and hazard risk management in Ghana. So, ladies and gentlemen, today she will share valuable insights on strengthening the seismic preparedness of Ghana's cities. So she's a Chief Emergency Preparedness Officer, the head of Geological Department at NADMO, National Disaster Management Organization. Ladies and gentlemen, Dr. Beta Kusimi, let's give her a hi.
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 Great, thank you. And last but not the least, our moderator for today, champion man, Engineer Michael Obing Kunedu. He's a chairman of the Civil Technical Division of the GHIE and a geotechnical engineer with over 35 years of professional experience. I mean, he's been practicing this since 1990. So he knows what he's talking about. His expertise spans geotechnical engineering, engineering geophysics, and he's ventured also into the water and sanitation engineering space with extensive experience in planning, investigation, designing, and implementation of infrastructure projects. He currently serves as the president of the Ghana chapter of the International Geosynthetic Society. And he's also a council member of the GHI, Ghana Institution of Engineering. He previously served as the chairman of the geotechnical group. That's the geo group of the civil technical division. So I've actually taken over from him. In fact, he played a key role in advancing geotechnical engineering practice and professional development in Ghana. He's a long-standing committed member to the development of geotechnical engineering, and this makes him exceptionally well suited for today's program to be our moderator on the discussion Seismic Preparedness of Ghana's Cities. So, ladies and gentlemen, our moderator, Engineer Michael Obeng-Konedu. Please, let's give him a hi as well.
Hi.
Hi.
Hello. Oh. Hello.
Yes, not too late.
Hi.
Yes, I'm just getting Mr. Opoku to join us. He is now here. Let me see. Oh, not yet, but I think he'll be in. Okay, so I would like to hand this over to our moderator, Engineer Konedu, to guide us through this important conversation. As I said, he's very experienced and we are delighted to have him today. So, ladies and gentlemen, Engineer Konedu, please, the floor is yours.
Oh, thank you very much, Chairman Jojo, for this nice intro. But as everybody knows, I'm not a nice man, but we'll manage. So greetings to all. I sincerely hoping that Mr. Opoku can join us so that we start from inside the earth, come to the surface and climb up the building. That would really have helped the discussion. So what do I do now? Jojo, do I give Mr. Opoku a minute or two, or we should come to the
Yes.
surface and then go back down there?
In fact, I shared the link with him just less than a minute ago, so I think he should be.
Yes, Michael, the design of
Yes.
structure starts from the top. So we'll start from the top and we'll go to the ground. So let's start from the top. Yes, let's start from the top. And when we get to the ground, we start mudding ourselves in there.
When small pools I'm chopping, I've even started now. They started attacking me.
Don't worry. I think he has joined. He's online. Mr. Opoku, can you hear us?
Mr. Nick Opoku, can you hear us, please?
Yes, I can hear you.
Super. You are very, very, very welcome, sir.
Thank you.
We've been waiting for you. Sure.
Yeah,
Now
sorry for
that
joining.
no problem.
All right, okay.
Now that you are here, we can start. That's very good. So I'll just jump into it. You see, we have very little time. We have a lot of questions, a lot of panelists. So without much ado, Ms. Ogogo, I'm coming to you.
Sure.
Okay, look. Ms. Ogogo, basically, my first question is, what is an earthquake and why should we be having this conversation?
Yes, so earthquake is part of the dynamic processes that takes or that goes through the earth. There are forces acting on the earth. And when these forces, the forces acting on the earth build stresses on the rocks. And when these stresses overcomes the strength of the rock, it breaks. And mostly it breaks along weak zones, which we normally refer to as the fault zones. And when it breaks like that, the stored elastic energy in the rocks is released in the form of waves. And as the waves passes through the earth, it causes to shake. And so it's this shaking of the earth that we refer to as an earthquake. Yeah. Yes. So I don't know if I've answered your question or there's more to it. Yeah.
You've answered the first part. I said, why should we be discussing this earthquake thing?
Yes. So we should be discussing this earthquake thing because Ghana lies in an earthquake-prone zones. And as I've said earlier, they are caused by fault lines. And Ghana has fault lines in the country. We normally call them the Pan-African Mobile Belt, which lies in the southeastern part of Ghana. And it's mostly those who know Accra and the southeastern part of Ghana. You see this mountain range from Weja through Nyanyanu, Weja, through Buri, and it goes all the way to Ho and parts of the Volta region. But the southeastern part of this mountain range is what we call the Pan-African Fault, and that's where our Kwapem Trust Fault lies. Unfortunately, these faults are not dead or inactive, and so they still keep producing earthquakes because they are still active. And once they have ever produced major earthquakes in the past, we have the 1862 Accra earthquake, 1939 Accra earthquake seems to be the return of the 1862, all with magnitudes approximately 8.5, which is quite a big earthquake to worry about. An earthquake have a return period, and so such earthquake can return at another time. And so we have the cause. And the fact that even from the 1997 6 March, we had a big earthquake. It was not that big, around 4.7. And recently, from 2018 to 2023, we've been having series of smaller earthquakes with the maximum being around magnitude 4.2. It tells us that our fault lines are not dead. They are still active. And so a return of a major earthquake such as the 1939 earthquake is still possible. And so that is why we still have to worry about earthquake and should form part of our discussion as we are having today. Yeah.
Thank you very much for setting the background for us. Thank you. I think I would like to outline the methodology a bit for us. There seem to be quite a number of questions. What I intend to do is to throw the questions to the panelists serially to the end. And after we get what everybody has to say, then I will open the floor for the general audience also to give you questions. I hope that is fine with everybody so that we can manage the time. Good. Having said that, and having listened to Mr. Opoku, I will proceed. When I was told that we will be having this kind of discussion, I did a bit of research into earthquakes, and what I found out that between 1935 and 1940, 23 countries worldwide experienced earthquakes with magnitude 6.5 and above. Now, out of that 23, 10 have had recurrences of similar magnitudes or greater within the last 10 years, 2016 to 2026. So quite a number of them have had a repeat of the same or bigger earthquakes. So my question to you, Mr. Opoku, is, based on our seismic history and recent monitoring, some of which you just mentioned, how imminent is a significant earthquake event for the city of Accra? Are we seeing any signs that suggest we are entering another high-risk period?
Well, we only, what we can say is that, like I said, there was an earthquake in 1862 in Accra, and it returned in 1939. So we are talking about approximately 77 years return period. And since the 1939, we've not had a devastating earthquake. And mostly, the further you are away you are from the last major earthquake, the closer you are getting to the next major one. Right. So, and this series of tremors we've been seeing these days, if we go through the report on the 1939 earthquake, you will see the details there that that was within during the British era. So if you go through the full details of the 1939 earthquake report, you will see that around the early 1930s, I mean, they saw a signs of increased seismicity, fault activities, and so they then governor wrote to geological survey to explain what is happening. And so what they said is that this series of tremors clearly shows that stresses are getting to a critical level. Probably it could, probably in the next 10 years or so, it's possible a major earthquake can occur. And in 1939, such an earthquake occurred. But we cannot conclude completely because predicting or forecasting earthquake is not something that is easy. But then, once we are far from the last major earthquake, and we are getting these signs, which sort of mimic what happens in the 1930s, which caused them to predict or to forecast that the next 10 to 15 years there could be an earthquake. It seems we are getting first signs. So that's why probably I can't give exact period. I can't say exactly that it's imminent, as if it's happening the next year or the next. But then the only thing we can say is that we have to prepare for any eventuality.
Thank you. Thank you. Our topic is about the seismic preparedness of the cities. Now, does the Ghana Geological Survey produce seismic micro-zonation maps for the big cities so that, I mean, it enhances our general earthquake preparedness in the infrastructural planning for our cities? Do we have that kind of background information we can refer to? Maybe in the form of maps.
In terms of side effects, we have a lot of information. Side effects mostly is based on to do your seismic micro-zonation studies, you need your site effects, maybe site effects where you take into consideration the geology, which areas will be amplified more in the event of an earthquake, what are our which frequencies within which such amplifications will be prominent, and all those things. Are we having things like areas prone to soil liquefaction? Are we having places? I mean, those things have to be clearly defined in a much more details to form the base, the site effects. And the micro-zonation it's not only about the site effects, it's also about the engineering aspect. So it's not only geological survey that should come out with a seismic micro-zonation aspect. So there's an aspect of vulnerability that will come into play when we're doing seismic micro-zonation, which squarely lies in the domain of engineers to see which buildings are vulnerable. And so when you have understood your site effects, the amount of, the level of shaking anticipated in different places, and then you have to look out for your vulnerability index. I mean, your buildings located in such areas, how vulnerable they are. So we need to get all these information together to be able to do that detailed seismic microzonation work. And currently,
Thank
we
you,
don't
sir.
have such detailed microzonation work. And I think it should not only be geological survey. Engineers and geologists should come together, or geological surveyors should come together to develop such a detailed microzonation map for GAP. And especially
Recently,
microzonation are normally done at the scale of a city. So probably I may say that a detailed seismic microzonation map for Accra and other big cities can also replicate. You can replicate it in other big cities as well.
yes, sir. So now
Yeah.
that recently you've been in the news that you've upgraded your seismic monitoring equipment.
Sure.
So what new capabilities does this provide you, and what additional information are we now able to capture?
Yes. All right. So earlier, when we installed our seismic network, we're transmitting the data through satellite system. And if you install seismic network across the country and you don't have a transmission system for it, in the event of anything, you have to be traveling to all your locations. Currently, we have them across the southern part of Ghana. You have to travel to all these places, Asankregwa, Kumasi, Weja, wherever it is situated, to manually retrieve data to process. So when we install them, we're using satellite transmission system. And I'm sure that's supposed to be the truth. We consider the satellite system because in 2012, when this digital seismic network was installed, we're not having internet coverage, or our telcos network coverage was not good enough in most of the remote areas where we have installed our seismic equipment. And so we had to rely on satellites. But the satellite had given much problem ahead. And so with the new system that we have installed, we have what we call it, convert from the satellite to a cell modem transmission, where you have a modem with a SIM card providing internet. And now almost every part where we have our remote stations installed have network coverage. So we are getting, so we have converted from the satellite to the cell modem, which is much more reliable and is providing data continuously to our central observatory in Accra. So one thing is that it's highly unlikely that something will happen and will not be able to detect it quickly and give early warning for early response. So in terms of the transmission system, we've upgraded them. And the challenge we're having was not only with the transmission system. We installed this, we procured this equipment in 2010 and installed them in 2010. We are in 2026. So it's almost 16 years old. And these days, one thing I've observed is that manufacturers these days do not manufacture things to work forever. They have what they call support. So at some point, some components lose their support, which makes it difficult to use them again. So most of the components forming our seismic network have lost their support. For instance, the satellite that we did the conversion, if we were supposed to continue with the satellite conversion, most of the signals transceivers have all lost their support. So we're going to go for a new one. And even when we look at the cost component, then it's almost the same as converting to the cell modem. So it's one of the reasons why we converted to the cell modem. Also, some of the seismic components, like the digitizers, had also lost their support. So we had to change all our digitizers to new digitize it. On the Akoso model, all the strong motion accelerometers installed to monitor the dams, which records ground acceleration. We had to replace all of them with new equipment, including the solar transmission system. So I would say that more or less about almost 85 to 90% of the setups, I mean, if you heard it in news, about 21 stations that were installed were completely new. The only thing we did not change were 8 of our remote stations. So we're having 8 remote stations which records ground velocity. So we have seismometers there. And we're having 13 strong motion stations which records ground accelerations, and we had accelerometers there. So all the 13 ground acceleration with the accelerometers, we changed everything and installed everything as if they are new. Not as if it's completely new. The 8 broadband stations which we use for our monitoring, the velocity sensors, we replaced everything except the 8 seismometers. And even with the 8 seismometers, we suspected that probably 1 or 2 of them may not function well when we upgrade them. So we even bought 2 new seismometers. And had to even, and when we were doing this, so we saw that 2 of the new seismometers, 2 of the old seismometers were not working, so we had to replace. So you could see that of all our 21 stations, the only thing that is old is 6 broadband seismometers. Out of the 8, we replaced 2 with new ones and maintained 6 old ones. So you can see that the network is highly upgraded and almost completely new. And through the cell modem transmission, almost all the data is transmitting to the observatory in near real time. And so we're not going to have a situation whereby there's something and we are struggling to go to various stations to manually retrieve data, to come and analyze them before we can come out with what do we call it? The earthquake parameters, such as the magnitude, the locations, and other things. So, and we also have installed one of the new, what we call processing and analysis software. Normally these days, the seismologists use AFCOM3, and that one have been installed, and so it's automatically detecting events, associating amplitude peaks, and if it's cut across, it declares an event and automatically posts the events. And we can have even what we call alerts on our phone to even show that, yes, there has been a tremor or an earthquake somewhere. So it's a big improvement in our over our earlier installations, which had almost broken down, because almost everything was not. We were left with just about 1 or 2 stations which were actively working. So that's the situation. So we have upgraded everything, and almost everything is single. I don't know
Thank you,
if
sir, for these updates. Thank you. Thank you.
okay.
It means that at least with regards to our Geological Survey Authority, the state of preparedness has gone up. Now,
Yes.
let's move to the
Let
domain
me
of
also add here that earlier our broadband stations, which were covering the southern part of our remote monitoring, so we were covering the what do we call it, the southern part of Ghana, were only monitoring ground velocities. But with the new system, we have added ground accelerometers to each station. So at each location, we have both ground, we have both seismometer, which records ground velocities, and we have accelerometer, which records ground acceleration. So at each location, we have both parameters being recorded. So this means that even in the event of a major earthquake in the future, we'll be able to have big ground accelerations for all these locations. It's not dense enough as we would have expected it, but it can form the basis through which you can do your zonation map to understand the acceleration levels at each of these locations, as well as the velocity, peak ground velocities as well. So it's a major improvement over the previous system.
Wow. Thank you very much, sir.
You're
So
welcome.
now we'll move from seismology to engineering. Prof, good evening. Professor Ampedu.
Hello. Good evening.
Yeah. Good evening, sir. How are you, sir?
I'm alive.
We thank God. We thank God. You know, I've been waiting for almost 30 years to get this opportunity. For now, I'm the
Okay.
one asking the questions and you will answer. It's a very rare
Yes.
opportunity.
Yes.
Okay, Prof. You see, I have heard somewhere that the role of geotechnical engineers in earthquake preparedness is often overlooked. Yet the ground beneath a city can determine whether buildings survive or collapse during an earthquake. In simple terms, a well-designed structure can still perform poorly during earthquakes if it is founded on unsuitable ground. Now, with this backdrop, I want to ask you a few questions. The first
Sure.
one is, what is the role of geotechnical engineers in earthquake preparedness?
Okay, thank you very much. I think the seismologist has laid the foundation, and we need to quite understand that civil engineers, we put our buildings and structures on the overburden, on the soil. The soil is sitting on the rock, and we put our buildings on the soil. The earthquake motion would be registered on the rock, and then it goes through the soil. Now, going through the soil, several things can happen. The soil can act just like an amplifier does and multiply the displacements or any any way that we want to measure the earth movement in the rock on the surface. Now, when you have a displacement, you have this amplification, if you want to put it that way. The soil column that is above the rock will undergo all the dynamic motions. And it has its own particular, if you want to put it, natural frequency. Now, if this natural frequency of the soil, that is your foundation soil, happens to coincide with the natural frequency of the structure that has been placed on it, then you will find out that it is as if the structure is being pounded by a much, much higher earthquake. And so you can get very, very, very serious damage to the structure. So the whole point is that what happens to the structure depends to a very large extent on the kind of material on which the structure is sitting. If it is sitting, let's say, on some kind of soft cohesive material, you are likely to amplify it. If it happens to be sitting on some loose cohesionless material, and you happen also to have quite a higher level of groundwater, then it's like petrol to matches. You could get the situation where, as we put it, your pore water pressures will be going up, your effective stress will be going down, and a point would arrive when you will have absolutely no bearing capacity. And so your structure will just collapse. And this has happened in quite a number of cases. The classic one that you have in the literature is the one that happened in Niigata, which is well recorded in the literature. But quite recently, 2023, the earthquake that occurred in Turkey, which unfortunately we lost one of our football stars. There were some cases where liquefaction occurred. And when liquefaction occurs, it has nothing to do with the structural integrity. It is a complete foundation failure. There were some high-rise buildings that just fell on its side. Even the glass didn't break, but the building just fell on its back and it was just lying down there. Complete loss of foundation. So when we talk about foundation and the geotechnical engineer is vital, very, very, very important, because that is where you will determine, based on the geotechnical characteristics of the material and a few other things, whether or not how that material is going to amplify or liquefy or do whatever it is to the earthquake that is coming. And he did mention about microzonation, that is not only just as a seismologist or geologist. You need everybody on board, and the geotechnical information is vital. That is why it's important that we have a good understanding of what lies below our city. Not just one borehole here, one borehole there, but put everything together and let's have a complete understanding of what is below the city, different parts, how the different parts interact. In the course of the discussion, I will mention the Mexico earthquake of 1985 as a classic example of what geotechnical engineering, the geotechnical material, can do if you miss the point. So to answer a very long answer to your short question, geotechnical engineering plays a vital role in whether we are prepared or not, because that is what is going to lead us to do a good job of microzoning our cities. That is what is going to help us plan, and that is what you need in order to work out how prepared you are or not.
So, Prof, then from what you're saying, it means that in the city of Accra, the same earthquake could cause different levels of destruction based on the geotechnical conditions.
Precisely, precisely. In fact, the same earthquake, sometimes it doesn't have to be even very, very far. It could be very, very close. If there is, let's say, a soft material lying next to a hard material. For example, you have a previous lake material, a lake that has been filled in. You have the interface from soft to hard. And it could be as close as just within 1 meter, 1 kilometer, or half a kilometer. And the response will be completely different, depending on the kind of structures that are in the area.
Interesting, because we've had engineers arguing with us that, look, the geological services for Accra, PGA of 0.2. So everywhere in Accra, they just make an assumption and design with that one value throughout. Are we saying that that is not a good practice?
Well, if you have the arrangement for me to show you one or two figures, I can make it a bit more clear in the discussion. So if that technical arrangement can be made, I will show you what is on my laptop. I put 1 or 2 slides, and then we can it can show very clearly what I'm talking about. So,
Yes. I think
yes,
you are a co-host, so you can do that.
I am.
Yes.
Okay. So where do I have the share?
So you can just
Ah,
show your
okay. 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 All right. Let me share with you with this one. Okay, with this one for us to try to understand. Can you all see my screen?
Yep.
All right. So
Yes,
this
Prof.
is, yes, this is part of Japan called Hokkaido. Now, there was an earthquake where you have the star was in the sea, 270 kilometers away. And where you have the little red dot, they did some measurements. The earthquake had a magnitude of 7.9. Now, when you look to the right, I don't know if you see my
Yes. Okay.
yes, okay. So you see this is 0.05 in the sandstone rock at 153 meters deep. So this is in the bedrock. The acceleration was 0.05 g. But on the surface, it was 0.35 g. So your seismograph would give you 0.05. But I did hear the gentleman from the is it geological survey talking
Survey,
about
yes.
the accelerogram. So you have that one will be on the surface. So you can measure the acceleration on the surface. So this one is what actually you need for your design, not the one at the sandstone at the bottom. That one would be in the rock, the base rock. And because your building is sitting or your structure is sitting in the overburden. So on the surface, you get 0.35. So from 0.05 to 0.35, you have something like 7 times. So that is what we are talking about. So even though I don't know, Accra, what we measure in the rock, if that is 0. Whatever it is, on the surface, it would depend on where you happen to be. So that's the point that I'm making. And let me show you. Yes, I will show you. This one is a Mexico one. An earthquake occurred and the cause was somewhere on the other side of the Pacific Ocean. And Mexico City is about 380 kilometers away from the focus was in somewhere down there. So effectively, the epicenter was just somewhere here. And this one is 380 kilometers away. So if you look at the right, so you see the source, 380 kilometers, you have Mexico City. Now, the damage that occurred in Mexico City was far, far, far higher than what occurred even in this city that was at the epicenter. And the question was, why? And if you look at the details, this is in Mexico City. Mexico City. They had accelegrams at various locations. That's why I'm happy to hear that they have accelerograms in the city of Accra. And if you look at the scale, you are talking about less than 5 kilometers. So at this one at the University of Mexico, at the Rock, they had 0.04. 0.04. Then, just like almost less than 5 kilometers away, they were measuring in one location, it was 0.1, but in another location, it was 0.19. And the distance was very, very short. So it can be just between Nkrumah Circle and the police headquarters. You could have very, very different. And when you take a look at the geological thing, this is what you get. You see, so at the university, they were effectively on the rock. Then they had different depths of very loose or soft material. And there was one of them, which was 40 meters deep. And that one was the one that amplified it. Of course, depending on it was a 2-second period amplitude, amplified it. And so you got worse effect here. Even in the deeper soft material, the problem was not there. The design that was recommended was 0.3. So it was okay for them, but this one was 0.9. So the building came down. The buildings came down in that area. And the effect was that. So you can see that within the same city, very short distance, same earthquake, everything. But because of the difference in the soil, you have completely different response. And they lost about 20,000 people in that location just because of that effect. So I think long answer to your short question is that is what we are talking about. Thank you.
Thank you, sir. You made it very clear to me that the geotechnical investigation report, especially one that has some seismic survey information, is very, very important for design of these high rises we are seeing springing around all over Accra. It seems we have to pay a bit more attention to these things. And references to generalized maps and things might not be the best way to go. Thank you for that clarity, sir. I want to ask you one small question, then I move to the structural engineers. What is the actual contribution of geotechnical engineers in preparation of seismic microzonation maps? What are geotech people supposed to do?
Yes, like he said, the point here is this, that if we are lucky, because you have your accelerometers that are installed, but if there's no earthquake, you have nothing to measure. So you don't have much to go by. So it is whenever there is an earthquake, then you can get to understand what really happens. But you can kind of use the geotechnical characteristics of the soil material to give you some kind of an idea about how the soil is going to respond using what is known as the response spectrum. You use it to kind of have an idea about how it's going to respond. And so, for example, if you you have the data for the geotechnical characteristics of the material, you may sit and be able to kind of guess that under the certain circumstances, if you are putting structures of such and such a thing, these ones are likely to amplify. And so you would probably rate the area differently based on the understanding of geotechnical characteristics of the soil and your understanding. You could use it to kind of do some analysis and come up with roughly kind of what you expect to happen. But to get actually what would happen, you need to have had some record that would give you some indication of how the soil will behave. But you just need to have it so that to help you in assessing whether the area is likely to amplify or to liquefy. For liquefaction is very well known. You can do the liquefaction potential and estimate that one fairly easily from routine SPT tests and so forth. But it is the amplification that you need the frequency response spectrum to help you do.
Thank you, sir. Thank you. I think now we must move away from the ground and look at the structures that are placed on the ground in Accra. So I'll move to the structural engineers.
Can I add a bit? Can I add a bit
yes.
before we move to the next?
Yes. Okay.
All right.
Okay. Please do.
Yeah. So what I want to add is that to your earlier question as to whether in Accra, if the PG is 0.2, everywhere it should be 0.2. You know, most seismic hazard map, I mean, it's normally specified that your ground acceleration or maybe the map with the coloring showing different acceleration contours, like maybe if it's 0.2 G, it's the same color, 0.15 different colors. So you have different areas showing colors corresponding to the accelerations. Normally, such acceleration values, normally they mention that is for a rock site. So you have a 0.2 G. So it means everywhere that is your base is rocky, then that 0.2 G applies. But then if it is a soft material, then depending on the thickness and how soft it is, will amplify the signal. So you need to take that. You can't use that 0.2 G as raw like that for everyone. You have to account for the soil amplifications, which will require that maybe your pre-ground acceleration values is increased a bit to cater for it. But normally, if we were to have acceleration records for most of our big earthquakes, we could have used it to develop this response spectra mentioned, which will tell you each location where you have done your recording, how much is your amplification factors, and within what frequency. Because the frequency is extremely important in setting up the height of your building to avoid resonance, as he mentioned. So if you don't know your frequency value for a particular site, whether it's 0.2 G or it's 0.3 or 1 G or whatever, sorry, not 0.2 hertz, excuse me, 0.2 hertz or 2 hertz or 1 hertz. You don't know your frequency, it becomes difficult to set the control the height of your building. Or every building has its own natural frequency. So how should you set your natural frequency of your building such that it does not match with the dominant frequency on the ground, so that to avoid resonance? And so sometimes these days, in most method that they use, if there's no actual earthquake record, is recording background noise. So normally, later on, maybe you can Google to read more on HVSR, horizontal to vertical spectral ratio, using ambient noise. So if you have a seismometer with your 3 components, you can record the background noise for a time. Then you can analyze the background noise by dividing the horizontal component, by dividing the horizontal component by the vertical component. It will give you the amplification factor. And this, before even that is done, your noise, which you have recorded, you have to transform them from a time domain, because you are recording in time domain. So you do your Fourier transform from time domain to frequency domain. And so if you get your time domain to frequency domain, you divide the horizontal by the vertical. And so you're going to get a ratio. So each frequency and its ratio. So frequencies that gives you a higher ratio is where your high amplification will be, or will be concentrated. And so you want to look at this entire spectrum to look at where there is a lower amplification. So those low amplifications, probably it could be 0.2 hertz or 0.3 or whatever. Then you match you make sure that your building natural frequency matches with where you have a low amplifications frequencies. Because if it matches with where you have your high amplification frequencies, then you're going to have a huge resonance, as you mentioned, and your building will shake maybe 4 times than normal, which may cause it to collapse. And so even if your ground acceleration is mentioned that it's 2G, it's for rock sites. So you have to account for the effect of the soil in varying your height of your building, and then in varying the strength of your building in terms of acceleration to be able to resist an earthquake at the site that you have chosen. So I don't know if I've added a bit to what
You have added more than small. You say you're adding small, but this one is more than small. I see that you are really in your domain.
Thank you.
Okay, Engineer Beverly. Beverly, are you
Yes.
there?
Yes, I'm
Yes.
here.
So we have naturally moved into your domain. For
Yes.
those of you who design these structures, in your experience, how well are buildings in Accra designed to withstand seismic activity? Do you take all these things that have been mentioned by the 2 areas speakers into consideration? If you say you do, I'll ask you where you get the information from. So the question is, do you take all these things into consideration when designing these high-rise buildings with these deep basements and things that is now appears to be almost common in Accra?
Okay. So we do, to a very large extent, as engineers, because it's required of us to consider these things, considering that Ghana is within a seismic zone, not high, but it's still within a seismic zone. And so we are required by design to include these things in our design. And it actually also depends a lot on the type of project. And so when we look at big projects like high rise, you've mentioned that a lot. Designs like airports, hospitals, embassies, large commercial buildings, you really have to consider these things if they are within Accra and the areas that are considered to be seismically active. The challenge here is that for designs that go to incompetent people, because clients are allowed to send their designs to whoever they want to, we cannot guarantee. But for engineers, we do consider these things. And Our information is usually from two sources: geotech reports or data available on the internet, in books. And so, yes, these are areas where we get our information from. On such big projects, like I mentioned before, high-rise buildings, airports, hospitals, and embassies, you will definitely have geotechnical survey reports available to refer to for these kind of information. For projects where these are not available, then we will rely on past records, what has been used in the past. Like you mentioned in Accra, for example, everybody says you use 0.2G for your PGA. And so if you're doing anything in Accra, you would use that. And so, yes, it depends on the scale of the project and the information available. But yes, as engineers, we do consider these things in our designs.
I want you to be a bit more specific. The question to you is, what is your sense? Is it something that a lot of people are doing, or just a few concerned people who are doing it? We want to, at the end of the day, appreciate the level of preparedness of the whole city. So commonly, do people incorporate these kind of factors into their design of structures? That's what I'm trying to tease out from you.
Yes, in the engineering fraternity, yes. Every engineer I interact with considers these things in their designs. But what I just wanted to add to this is that people consult non-engineers for design. Okay, and so I can't speak for that. But as engineers, yes, we do consider these things in our designs.
You mentioned certain kinds of projects, and I will call those as an important project that
Yes.
people pay a lot of attention to. But we know from all over the world that when earthquakes do happen, a lot of the damage and the suffering occurs in areas where the people are not too important and their dwelling places and things are not well engineered.
Yes.
With that kind of background, would you say that our buildings generally are safe for big earthquakes?
For designs that are coming up in recent times, big or small, earthquake is considered in the designs. For existing buildings, you can't say so much because engineering has evolved over time. Now it's even easier to do earthquake design because of the use of software and all that. It was more difficult in those times to do such designs. And so even in developed countries, they are now looking at existing buildings and to see how they can retrofit them to be able to withstand some level of seismic activities. And so, yes, for new buildings, earthquake is being designed for in such buildings. But for old buildings, for the most part, what in my experience and in structural analysis or structural integrity surveys, you notice that a lot of the buildings have not been designed to withstand earthquake. And so, yeah, for new buildings, yes, there is earthquake included in the designs. For old buildings, not so much.
Okay, let me reach out to Michael. Michael, are you there? Engineer Michael Zadok. Engineer Michael Zadok, are you on the panel today? Okay, then I'll go back to Beverly. Beverly, what about roads, bridges, flyovers, transportation, infrastructure and things? Do our current building codes address this kind of infrastructure in a meaningful way when it comes to seismic resilience?
Yes, in terms of design, it does. The Eurocode, for example, Eurocode 8, is focused on designing for seismic action for all types of buildings, for all types of structures. buildings and bridges. And bridges especially, there are very rigorous requirements for seismic design for bridges and flyovers and such capital intensive structures. And so yes, there are provisions for design in that. But I keep stressing design because when it goes into construction, it's a different conversation.
That's so.
Yes, because
Okay.
design. Okay.
You refer to Eurocode 8, which I know is an international code. The
Yes.
Ghana Building Code. I
Yes.
believe there is a Ghana Building Code. Does the
Yes,
Ghana
there is.
Building Code also address it in such a meaningful way? Are you aware of that?
Yes, the Ghana Building Code does as well. I refer to the Eurocode 8 because it has been around longer than the Ghana Building Code. And in fact, the Ghana Building Code doesn't depart from the requirements in the Eurocode.
Yeah,
What
yes,
about
Mike, can I add a little bit to what Beverly is saying?
Prof, please add.
Yes, I think the point here is this, that once you have a code that you are following, half of your problems are solved, because a lot of the thinking has already been done and placed in the code. It is only whenever there is an earthquake and something doesn't work well that we go back and then we modify the code, like what happened in Japan after the 2010 big earthquake that caused the nuclear reactor to explode and so forth. They come up with improvements in the code. Our major problem, as you will see, is not the code, but is the way we do things. The typical example is the difference between the effects of the earthquake that happened in Haiti in 2010 and that same year what happened in Chile. They are in the same region. The Haiti earthquake was much smaller than what happened in Chile, and yet Haiti lost hundreds of thousands of people, while Chile had just a couple of thousands of people. And the difference was just the earthquake preparedness and the code. Whereas you will say Haiti, they do things just like we do things here. You build anything, anywhere, anyhow you want, and you live in it. And so when the earthquake comes, it demolishes everything. But in Chile, they had strict codes that they had to they had to stick to, and that guided us. It guided them in what they did. So even if they did lose, yes, but most of their lifeline structures, that's what she's talking about, your bridges and so forth, they are lifeline structures. Your hospitals, if everything fails, those things should still be there, at least for us to carry people over to Kolebu. Kolebu shouldn't go, it should stay. So we got to make sure Kolebu is properly engineered. Then the bridge that takes us to Kolebu must also be there. Otherwise, what do we do? So there are certain lifeline structures that are so critical that when we are designing, there shouldn't be any, corners that we are cutting. But like she said, the key thing here is the code. And if you are staying with the code, at least half your problems are solved. Thank you.
But then my next question actually was, how robust is the current permitting process for screening for seismic safety standards for building projects? I mean, are we like Chile or we are like Haiti?
Is it to me?
Yes, you brought those two names, so please deal with this.
Oh,
Are we like Chile or we are like Haiti?
But in Ghana, do we have a screening process?
We go through a permitting process, and seismic safety is part of the process.
Yes, but it's only, but everybody is building all over the place without
Yes.
going through that thing. That thing is there only when you have one or two big, structures here and there. But otherwise, where the majority of people live, everybody is building anywhere, anyhow, and nobody is taking care of it.
Prof, you have answered the question. Don't worry, I get the drift. So now I'm
Yes.
coming to NADMO. Now the engineers and the seismologists have talked, but it is NADMO that is responsible for taking care of us. So, Doc, I want to ask you a few questions. May I proceed?
Yes, please.
I saved yours for last because, in fact, I think your questions are going to be the hardest, but you are used to disaster and things, so you can handle it. Well, I seem to remember that Ghana has a national framework for earthquake preparedness and response. Look, we do have something like that, right?
Yes.
What is the current state of that framework, and what is the level of interagency coordination in that framework?
Okay. So thanks for the question. That framework came about after consistent earth tremors were recorded between 2018 and 2019. Then the then presidency instituted a committee to come up with refocusing Ghana's earthquake preparedness and response. So the document was produced. Then in the document, some recommendations were made. And those recommendations were again taken back to the presidency because it needed, funding to make sure that the recommendations were instituted. So a budget was attached to it, and then it was sent to the presidency. And even they requested for it at that time because we kept on between 2018 all through to 2023 thereabouts, kept on having the earth tremors in a consistent manner. And the most of the country's critical infrastructure seems to be on the fault line. We have the Akosombo Dam, even the presidency, the Flagstaff at Parliament, Pedrase, all these critical Wager Dam. And so as soon as there's a tremor, it then reminds them that something needs to be done. Then they will come that, oh, let's get a budget for it. We take the budget and nothing really comes. So NADMO took upon itself to look at the low-hanging fruits that can be done by the institution. And also that lies within our mandate. And one of it is awareness creation, education, sensitization. And so from there on, that's not also to say that prior to that document, this was not being done. We can talk as far back as us having some earthquake guards being installed in these earthquake-prone areas, and we did that together with UNESCO and Ghana Geological Survey, and these earthquake guards were placed in communities or environments where we know they are prone to the disaster. So we have one in Wager, the assembly, the earthquake guard. We had one also in Parliament, Pedrase, and then even NADMO head office. So prior to the document, we were already trying to get some some things, done concerning earthquakes in the country. But as we all know, preparedness is a process. And being prepared, you need to involve some planning, some mitigation measures. We need, of course, the awareness creation and all that. So we are on it. But we should also remember that no one nation is, fully prepared, for disasters. And that is why even sometimes in well-developed countries, they have, when there are disasters, they do have, external interventions and all that. So to bring it to a nutshell, yes, the document is there. A lot of recommendations were made, and we are hanging on the low fruit, and we are trying to implement them. So we are catching the children, Ghanaian children, we are catching them young. We are going to the schools, doing the sensitization and the education, doing the drills, engaging them to know the do's and then the don'ts. With the help of UNESCO, we came out with some material, some educational materials, some posters, some short videos, and even these videos were being aired on GTV. A few, I think some were 2022, 2023. It was very consistent, and so we are doing our best.
Michael, have we lost you?
Engineer Kunedu.
Oh, sorry. I was asking that apart from NADMO, which other organizations are part of this National Disaster Preparedness Framework thing? Doc, can you hear me?
Yes, sorry. I think we had all our stakeholders being part of it. The Institute of Engineers was part of it. We had Ghana National Service. We had the police, Ghana Police Service, the ambulance service. So, and most these are the frontliners when it comes to disasters. So we had them as part of the committee that came up with the documents, and we had the geological survey part of it. And yeah, I think basically these were the institutions.
Okay, so still want to know a bit more about the mandate of NADMO. Does NADMO have any preventive mandates? For instance, we've been talking about buildings, designs, what should be done, and all these kind of things. Is NADMO in any way responsible for some aspect of that, either with regards to siting of buildings and that kind of thing? Apart from responding to a disaster and then maybe public education, what other activity does NADMO
Yes.
engage in? Yeah.
So yes, NADMO predominantly is a coordinating agency. So we try to coordinate all the other agencies. We have advisory technical committees that when we identify or we suspect anything that is looming as a disaster, and we rely on them to give us that technical advice, and then it's forwarded to the appropriate institution or department for onward engagements. So we don't have the mandate to, our law doesn't give us that, that mandate to, for instance, bring down structures or even, go beyond giving the advice. Of course, we are trying to see how best we can amend some of these things in the process. So
Oh,
that.
thank you. Now I am going to ask you the question that everybody wants me to ask you. Whenever they hear NADMO is coming, this question must be asked. So I'm going to ask you, and then you do your best to assure me. Now the question states, if Accra was to experience a magnitude 6.5 or greater earthquake next week, how prepared is Ghana's disaster management system to respond in the critical first 24 to 72 hours? And in your experience, what are the biggest gaps that still need to be addressed?
Yeah, this is really that is the question you have asked. But like I said earlier on, NADMO is within our mandate, we are doing our best to continue with the education and the sensitization of the people. And we have had a number of simulation exercises, and then a lot of education is still ongoing. But if that should happen, as I have already said, no country is fully prepared. It's a process. Being prepared is a process, and it involves planning. Let's also ask ourselves, how planned are our cities? What is country planning doing towards the planning of our cities? What are the engineers doing towards the building and then the structures that we have? All these things, arrows into the question you are asking as to whether we are very prepared or not. So we need to look at the causes, from the roots. And if as a nation we do the right things, then I think we can build upon it. And then I think yesterday we had Venezuela and California experiencing earthquakes between 7.5 and 5.6 respectively. And it's still counting. About over 100 people in Venezuela are dead now, and it's still counting. So I think we are, as a nation, we are sitting on a time bomb. It's unfortunate that earthquake preparedness is one area that much attention hasn't been given to. There's this laissez-faire, attitude towards earthquake preparedness because it doesn't often occur as compared to flooding, and all other disasters. And so more attention is being given to those ones. But we are forgetting that with one incident of an earthquake, the whole country or the 5 regions that fault line passes through and especially where we have most of our critical infrastructure in Accra on this active fault line. The country is going to be on a halt. So we are still working around the clock. And as for NADMO, we have the EOC, that's the Emergency Operations Center. It's fully furnished. it's in the head office, working 24 hours. We also have our search and rescue team for immediate response. They are also, working on 24, that's around the clock. So yes, with response, I mean, they are there to give that response. But of course, the challenge is that we need to improve upon our training, capacity building, so that, they can effectively respond to some of these emergencies, especially, earthquake emergencies. So I think this is all that I have to say. I don't know whether I've answered your.
Oh, you have done some. You have done some. What can you
So
say?
which one is left?
Okay, so basically, these things, it is only when it happens before we can really confirm whether we are prepared or not. So we know once you say it's a process, so we believe that gradually you would be ramping up in terms of emergency shelters, medical search capability, all those things. It will happen in good time. Now, we've reached a point where I think the general audience must be given an opportunity also to ask some questions. And I would request, Dr. Ayer,
Yes, I'm here.
do you have any questions online that you want the panel to address?
Yes, so I think the first hand has shot up from, I think it's Engineer there.
Okay, so let's allow him to speak then.
All right.
Engineer
Thank you.
there, please pose
Yes,
your
sir.
question.
Thank you very much. I have one question for Nadmo and then another question for our structural friends. Nadmo, I think this language of we are doing our best tells me that though you are working, but you are highly stressed. Is it because you don't have the necessary logistics to work with? That is my question. And then our structural friends. It appears normally what you require in a geotech report to assist you do design based on seismic philosophy. And I think that with our friends from Geological Survey, the development of PGA, I believe that the system has to look at it comprehensively. It's a systemic work. We cannot leave it to Geological Survey alone. Nowadays, most of the geotech investigations, we have geophysical inclusions, and we have some data around. I think it's high time we looked at gathering all these data and start developing this microzonations map, because it's going to really help us. The choice of PGA has serious consequence on structural design and then the economy of a project. So if we tend to be choosing any PGA that we think that maps are giving us without probably attending to site-specific ones, it means that we may be doing too much of structural designs, and we may be giving a lot of cost to the client. So geological survey can be a lead here, whilst the data that we have is a progressive thing. We can start collecting data as we develop a map, so that at the end of the day, maybe in the next 2, 3, 4 years, we can have a comprehensive map as our PGA guide. So these are my comments and then the questions, please.
Hello.
Can we
Yeah.
take about 2 more questions before they start answering, please?
Okay.
So are there any other questions so that we could then manage them in lots?
Maybe
If
Mike,
not,
let me quickly come in. Prof showed a chart that started with a PG of 0.3 or 0.5 or so, and then it shot up. So now this thing should tell us that, okay, let me ask the question this way. So which PGA do you choose depending on your foundation depth? Are you going to choose the surface PGA, or you're going to choose a PGA That is based on the profile. So this question goes to Prof.
Okay,
Yeah,
so
Mike.
for now, we only have one question. I think
We have two. One for NADMO, one for Prof.
And then one for the structural.
and then one for structural, yeah.
Okay, so three. So let's deal with
Three.
it.
Okay, then let's start with the NADMO question.
Okay.
Can I make an input because I have to go now, unfortunately?
Okay,
Okay.
Yes, sir.
Yeah. Sorry. I think the point here is that actually the peak that is recommended is actually for the structures, for the structural design. So based on taking a whole lot of things into account, you will then, as I think, was it the geological colleague just recommended, whatever you see in the rock, you will have to take it as this is what we have in the rock. And in the light of what we have, the type of material we have, the conditions and so forth, I would recommend we probably bring it up to for 0.35 to maybe 0.4, 0.5. That would be the way to go in the absence of any other thing. But because the building is sitting on the what do you call it? Is sitting on the surface, for the structures, it would be sensible to use the PGA that you have on the surface. In the case of the Japan, they had piles and they had installed accelerometers on the different levels. So they had a complete record of what the condition was in the middle of the formation, at the bottom, and so forth. And so it becomes easy for them to decide what to use. But for us, we don't have, even the surface one, we don't have. We just be able to have just what is at the bottom. And what is at the bottom doesn't tell you what is going to be at the top. And that's where you need to come up with effectively a reasonable guess as to what would happen and do it this thing. But the warning is just don't use only the value that you have in the rock, because your building is not sitting on the rock. So
yes,
I
Prof.
think
let me just quickly add that if you have ever seen a comprehensive geophysical studies at a site, the site we are using, let's say 30 meters now, VS30. You can clearly see the profile from the 30-meter depth coming up. Okay, you see, assuming that, let's say from the rock you are getting 0.5, you can see the amplification coming up from the ground. So now my question was, assuming I'm doing 2-level basement, which you are looking at probably 7 meters, 8 meters down the line, do we need to use the PGA at the surface, or we're looking at the profile, we can cut off the PGA at where the profile is at, let's say 8 meters? That was my question.
I wouldn't know immediately, because what is at the surface you don't have. You are only guessing. So you would probably come up with a reasonable guess and use an average value, because 2-level basement, you are talking of something like just 6 meters. Is that not it?
About 8 plus the footing. So you are looking at about 8, yeah.
Yes, you are just about 8 meters. So it may be safer for you to use what you have at the top, unless you have, is it further and better particulars? It may be better to just stay with the maximum values you have at the top.
Okay.
All right. So, Mr. Chairman, with your permission, I'd like to go now.
You are
Yes,
ending my once in a lifetime position where I can question you is being brought to an end.
then you need to make another opportunity.
Okay, sir. Okay, sir. Thank you very
All
much
right.
for your contribution.
You're welcome. You're welcome.
So, Mike, structures, and then I think NADMO.
So,
Engineer,
yeah,
Engineer Beverly, if you could
yes,
pick up
I'm
the,
here.
okay,
Yeah.
please answer to the man's satisfaction.
Okay, so the question was, is it just the PGA we need from the geotech, if I'm correct?
No, I was asking, what do you normally, I know that there are challenges, right?
Yeah,
For example, there are times you will not be part of the team at the initial stages when even the geotech scope was being developed.
yeah,
So you come and meet a geotech report, but here you are doing an investigation. Sorry, you are doing a design which is based on seismic philosophy. But generally, I
yeah.
was asking, assuming you want to do a seismic design, what do you want from the geotech engineer?
Okay, so I mean the PGA is what we usually know to be very common because it defines the seismic hazard at the site. And so that is quite important, and we've established that. You also need the site classification, which will tell you whether the site is rock, is dense, is stiff soil, is clay. You need that information. And lately, what I have personally done is to ask that they define it according to the code, because the code has descriptions. Normally, the geotech reports would go through the profile, and then the geotech engineer will give his description, which is not wrong, but sometimes it's difficult to fit it into the description of the code so that you can be able to also pick other requirements based on the ground type or the site classification. And so the ground type or site classification is also important in this case. And then another important thing is the response spectrum. What we have done over time is to use the standard one provided in the code. And so there is type 1 and type 2 depending on the magnitude of earthquake. And
That's where the problem lies. You
yes,
see,
yes,
because
yes,
if you run a geophysical study and you are coming from the rock, every layer has its own response spectra. Every
yes,
layer. If you have 3 layers, they all have their various response. So the question is that if you have all of them, so you can use one as a critical one, probably the one that is vulnerable. Okay, then you can use that one. But that's where probably if you don't have it, then you go back to the generalized one that has been developed. And so this is a loose one, use this. This is a dense one, use that. But
yeah,
that may not be a case for a particular site, let's say in Ghana. So
yes.
I asked this question because I know Mike has been helping us, especially because he sits on some of these application principle, that we need to talk to the architects. Okay. It's not just asking a geotechnical, go and drill and give me bearing capacity. No, that is not what we want. And the structures too, please. It's not just asking a geotech engineer, I need a bearing capacity. That makes your work complete. No, that's what we need, a report that really characterizes the site and speaks about the site. And then it goes beyond the normal bearing capacity that you can have a foundation that can pass bearing capacity, but you have problems with settlement. You understand? So especially with this kind of high-rise buildings that is coming up, looking at their spans, you may have problems with this, what do you call it? Is it torsion or distortion or whatever that you are looking, or angular torsion, let me call it that way. So we need you to help us, especially if you structural engineers are part of developing, a design framework. They need to let the client know the requirement that they really want to help their design so that a proper geotech scope can be prepared and an investigation well executed. Thank you, Mr. Moderator.
So,
So in
I think,
terms of developing a response spectrum, I think that is a tall order to require from a single geotech engineer. I think this is something that should be a national exercise that should be developed so that we have that information. So this will form part of the micro zoning process so that it will be developed for specific areas because it's a lot of information to require that a single client should pay a single geotech to develop. It's a matter of research and production of such
Oh,
information.
the tools are available verbally. for a particular site, it can easily be developed. It's part of the geophysical investigation. It's not any tall order, honestly. So don't worry. The tools are now available. Geophysical tools are now available in this country. So don't worry about that. It
Okay.
shouldn't be a problem.
All right.
Yeah.
Okay.
Maybe
Okay. So
we'll have other sessions where we show what is currently available.
Okay.
exactly.
So that
Exactly.
practitioners will listen. So Chairman Jojo, please take note of that. Dr. Kusimi, we were for you to respond to something so that we can move.
Yes, I think my question has to do with why I made the statement of NADMO doing its best, whether it has to do with logistics or, well, it's a multifaceted problem. In the first place, I mean, why should our assemblies give permits to people to even build in, earthquake-prone areas? Not considering the fact that we even have to give buffers of 150 to 200, on both sides of the fault plains. Okay, that is a question to be answered. Now, the buildings are there and we have to, be prepared for any emergency. Here's the case, there are other disasters even occurring as we speak. Let's all be true to ourselves. Right now, we know about the flooding issues that are happening alongside landslides, building collapses, and all these are happening around the same time. And we are responding to them though. But in every organization, definitely enough logistics will go to these areas because that is what is happening. And then, it will be the institution will try or attempt to solve the problems around that area. Of course, the logistics needs to be shared across all these events that are happening. And so if yours is something that we can't really tell exactly when it's happening, then much attention wouldn't, be given. Though everybody knows at the back of the mind also that, it can be very devastating if it should happen. So that is where we find ourselves in. The political will is not there because immediately after the floods, mind you, we have Ebola. Coming in, some of the African countries are already experiencing it. Right now, we are doing our education and sensitization, so that we won't have to record Ebola. That wouldn't end, and you will hear of fires occurring. That wouldn't end, and we have our pest armyworm infestation in the north and other. So the disasters are quite many. The occurrences are happening, and so I think as a nation we also have to help, as individuals we have to help ourselves, and we should also try to do the right things to avoid some of these things. Some of these things are quite avoidable. That's all I can say. Yeah.
Thank
All right.
you. Thank you. Jojo, if there are no other questions, can we ask the panelists to give us their closing remarks?
We had a question from Engineer Boating.
Okay.
Jojo, I also have a question.
Okay, so we'll take Engineer Boating, and we are privileged to have the past.
Oh, but George, before you go, Mike, Zodak,
Yeah.
I think Michael Zodak is online, or are you going to allow?
The time we needed him, he was not there.
Yeah,
Now
we couldn't get him.
He just sent me a message that he had problems beyond his control. So let's spare him this time.
Oh, okay.
Okay.
Dr. George, I also have a question. All right. So we'll take Engineer Boating. Are you here?
Yeah, I'm here.
All right.
Actually, mine wasn't a question, but just to add on to what Engineer Joe said about the response spectrum. It can be determined. At various foundation depth, all one needs is that you provide information at which depth you want to put all your foundation, and that can be done because you can come out with a VS within that particular layer or medium, and then use some earthquakes, series of earthquakes that are present, whether here or probably of various magnitude that could be acquired, and use that in your model. That should be able to give you a spectra within that depth. So the civil engineer will use that spectrum to determine the 1 second, the short period, and then the 1 second period, and read off the pseudo spectral acceleration that they will need for their structural seismic designs. Thank you.
Thank you very much.
Jojo,
Dr. Chakli.
Jojo, at this point, let me invoke executive privilege. Why?
Okay.
Past President Engineer Kalian
The
wants
hand
to
is
make
up.
a comment. Yes, so please. A hand for me supersedes all the current hands. So, Madam, please talk.
Thank you. Thank you very much. It's been an interesting discussion. Mine is very brief. I just wanted to say that when we are talking of low-hanging fruit, there are some very, very low-hanging fruit. Number one, every single utility, every single major organization in the country should be written to and told that all your facilities should be prepared for earthquakes. Then, in fact, the utilities should be asked the question or given a standard that we want you to be back up. ECG, when there's a major earthquake, we want you to be back up in 75% of the places within 30 minutes or something like that. MTN, this is what we want from you. Every Vodafone and so on. Sometimes we try to take on everything and pass it on to government. And the organizations also have responsibilities. And I think NADMO should be writing to every single one of them. You'll be surprised that they are not aware. This was a finding in our report. They are not even aware that some of their masts and so on should have been designed for ground accelerations. They are not even aware. So they need to be specifically told that we are in an earthquake zone. And the implications are that all your equipment, everything should be able to withstand earthquakes. And when there's a major earthquake, because you are so critical to everything, we want you to be back up within this limited time. Even our bridges and so on. Nobody has specifically told highways. So they are doing, depending on which engineer is in charge, they will do something or other. Somebody needs to specifically tell them that we are in an earthquake zone and this is what we expect of your bridges. So over to you. It doesn't cost money to write these letters. And I wish that GHIE would take it up with NADMO to help them write these letters. Thank you.
Thank you, Madam. Jojo, we are back to normalcy. Please continue.
Thank you. All right, Dr. Chakli, then we'll come to Dr. Zambai.
Okay. Thank you very much for the opportunity. I have a very simple question. In our discussion, we had two values for Accra. I had 0.2 G for Accra. I also had 0.35 G. And Prof even chipped in 0.4. So from our engineers, what is the recommended one for Accra for those who cannot conduct the seismic investigation and generate a response spectrum? What is the recommended one? Because the code is saying 0.35 G, and now most people are using 0.2 G. And why?
So who answers?
Jojo,
Yes,
Okay.
I'll answer.
Okay. Hey, Nialote.
Yes, sir.
Go ahead. Go ahead.
Yes, I will I want us to refrain from recommended figure, like Engineer Boatin made mention of, and then Joe or there you have also mentioned it. Once the tools are there, the equipment are there, why don't you go site specific instead of saying that you don't have the figure So we go to a standard ones. The standard ones cannot help us. Once the tools are there, let's go site specific. Each time we want to do the foundation, let's go site specific. Let's get the geophysics guys to give us the figures we need at the depth of the foundations we want to go. And then we shall be better off.
Moderator, can I add to Engineer Lote's comment? Am I
Please,
permitted to
short.
Okay.
You have a habit of
You
talking
know,
plenty. This one,
yes,
make
well,
it
you know
short.
that I'm a lecturer, so don't worry. You know, I remember some time ago, either I was doing some job for some Turkish guys, and Accra were talking about 0.2, 0.35 G. They were so much say, really? Even in Turkey, they use something less than that. Where we know that, you know, when it comes to earthquake issue, it's more prominent than what we use here. So, and I think that we should be thinking about how our, what do you call it, microzonation was done. But probably, I don't know if Nick is still here. If he can tell us how we develop our microzone, it would be a very good start for us to see whether those times they were constrained. I have chance upon the literature that tells me, especially when we're doing our how do we call this? Mike, how do you call this? Between 7 and 8. What's the name for that? But I'm trying to forget. Not the zonation. You know, they tell you that Ghana Accra lies between 8 and 7 or 7. Using the Roman numerals. Intensity, exactly. You know, you know, those times we were using that, and I remember that the document was talking about how we developed. It was mostly based on perception, based on this our 1939 earthquake. Yeah. You know, and it's something that we have to look at, because if you look at 1939, the kind of buildings we had, where we had a considerable, you know, structural challenges, it's not the kind of buildings we have now. Okay, so I think that it's high time we went back to look at it and start developing a new one. So for now, to Dr. Chackley, maybe you still have to go with the code. If you don't have, you think that you don't have, let's say, the money to do geophysical, then you have to rely on the code. That would be
no,
safer.
Joe, don't tell that to Dr. Chackley. If you are going to build, you must prepare for all the costs. And from everything that has been said today, Dr. Chackley, there's nothing like affordability matter here. If you can buy cement, you can do the correct testing or the foundation things before you build. It's critical. This time we cannot go around corners again. I beg you. And you see,
the reason why I asked the question is because even though we agree that you must go site specific, we know geotech is not an exact science. So even when you go site specific, it's possible that these values may be exceeded. But we need codes as a general guide for everyone. So if the Ghana Purdue code is saying 0.35,
Doc, remember, codes are minimum requirements. They are not the cap.
Okay, I agree to that. So if the minimum requirement is 0.35, let's say it's 0.35 G, and now based on recent knowledge, it needs to be updated. Why is Ghana Geological Survey not doing anything about it? Why is it still 0.35 G?
Your response would be appreciated.
Nicholas, please take this one on, and as you respond, give us your closing remarks. Then we go down the line, right? The way the guys have heated up now, if we don't control it.
It's true. So our time is fast.
That is one of the main reasons why we cannot afford to live in without a seismic network continuously monitoring efforts. You see, all these challenges has come about because the major earthquake, which is the 1939 earthquake, was not instrumentally recorded in Ghana. If we had instrumentally recorded them, the records are there, the amplitudes, the acceleration values, and everything are there. These debates wouldn't even arise at all as to whether which appropriate PGA is appropriate for the design purpose. You see, so because we could not record the 1939 earthquake, that's where the challenge is coming. The recent values that we have recorded is way below magnitude 6.5, which is associated with the 1939, magnitude 4, magnitude 4.2, 4.5, you can use that as those acceleration values for designing, you see. So that is why I'm always not happy if our network is not working. Because if a major earthquake like the 1939 earthquake happens, and our system or no monitoring system is able to record them, and we can't give engineers the true values of the earthquake, I'm sure we'll do ourselves a great disservice. So that's one of the reasons. So we are having that challenge because we don't have. So the debate will continue, even whatever scientific work that is done to arrive at any PGA value, it will still become a bit, because either you are going to rely on models from other countries, your data is not giving you that big acceleration values. What I mean, your recorded data is not giving you that big acceleration values from which you can reliably say that, yes, this is the value that we are going to use. So the debate will still go on until probably the next major earthquake, when we're able to record it.
When is it coming?
Before we can confidently say that, yes, this is what is the optimum or the appropriate values to be used for design. So so that challenge will continue to haunt us for a long time, because we could not record those efforts. And I also want to the misconception, Mr. Ade, Mr. Ode, don't let us conclude that the intensity values you mentioned were probably overestimated, because buildings then were not strong enough or whatever.
No, I
Even
didn't say that. I didn't say that. I said they were, if you look at how it was developed, they were mostly based on perception, because when they were doing their data collection, they were asking people, how did you feel it here?
It's not only based on asking people how you feel them. It's those ones comes in where there are no physical, what we call it, maybe we have a building collapsing. So they assess the strength of the building and the level of damage to assign those intensities weight. So it's not only based on going to ask people how did you feel it, and based on it you assign what we call it, intensity. It's based on damage distribution assessment. For instance, you have a Wager Dam, because at that time Wager Dam was well built. So if you have trusting of some parts of the Wager Dam, based on the level of the damage, then they will use it to assign values of intensities. There are guides to that effect. So you only have to assess whether it's the building so weak and it got damaged. Probably then in that case, you may assign a lower value. Was the building well reinforced, like the Wager Dam, and it got damaged? Then based on that, they assign intensity. So the intensity were assigned based on the damage distributions of buildings. And those days they were the whites who did, our colonial masters who did those things were well trained and very knowledgeable. And so they took a lot of these things into consideration in coming out with those intensity values. And it's those intensity values that has been used to develop what I would say deterministic seismic hazard maps, which is based on worst case scenario of the 1939. And another challenge we have now is now the engineers want to introduce some level of, want to use what we call the probabilistic seismic hazard assessment whereby you look at certain probabilities and what have you, in inculcating some level of risk into your design and those things. And so that is where we've probably not gotten there yet. And we are working towards to see whether we can use our little data that we have and other models from other countries, combine all of them to come out with a clear probabilistic seismic hazard maps, where if you want a 10% probability, 1%, whatever, with a return period of 50 years or 100 years or 400 years, you can develop such a probabilistic seismic hazard maps so that it can be used for engineering. And that is what we've been discussing with Madam Carlin and all the group, and we need to give it the necessary support and funding so we can work towards developing the probabilistic seismic hazard map. That probably maybe we may have confidence or we may find it much more reliable to use for inculcating into our building codes and design standards. Yes. And I also want to end by saying that earthquake preparedness is not only the responsibility of government agencies. We should bear that in mind, that in reality, preparedness is a shared responsibility. It involves government, engineers, planners, schools, businesses, communities, and even individual households. We all have a role to play in making sure that we are well prepared for earthquake. Thank you. So this is where I'll end. If any further questions come, I'll respond.
Thank you, Mr. Nick, for winding up for us. Engineer Beverly, your closing remark.
Moderator, don't forget me.
Do you want to contribute?
Yes.
Okay, then please say what you say. After you, then Beverly will give us her closing remark.
Hold on, we
Yes,
had a hand earlier, Dr. Zambai, and you made him stop so that Madam President will speak.
Yes,
Joshua,
good evening.
let Dr. Zambai speak, please.
Yes,
okay, sir.
good evening.
All right.
Yeah. In fact, I joined the discussion quite later on. I didn't. Is there any seismic profiling of the northern zone, especially the northern sector? I didn't hear that from the discussions. And then, what are the seismic situations within the northern belts?
Yeah. So the northern belt largely falls within, geologically, largely falls within our West African craton, whilst the southeastern part of Ghana falls within our mobile belt. We normally refer to as the Pan-African mobile belt. So seismic activities have been more intense within the southeastern part of Ghana, and Accra in particular, because of the coastal fault lines in Accra, has been much more. So, but for the north, because it's more within the West African craton, the craton is considered as a relatively stable part of the earth. And so we normally do not have, we hardly get earthquakes in those areas. But that does not mean that those places could be completely isolated from earthquake effects, because the earlier presenter mentioned the Mexico case where earthquake occurred 200 kilometers away from, I don't know whether it's 200 or whatever kilometers, or far from the Mexico City, but much more disaster occurred within the Mexico City. Even those closer to the source of the earthquake did not experience much disaster, because they were on a much more competent ground. Whilst those in Mexico City, which was formerly a lake, so it was prone to high amplifications, as we had a lot of disaster associated over there. So we are not completely ruling out the fact that maybe a major earthquake in Accra cannot have an effect in the north. But then if you go by the intensity distribution that I mentioned, you see that from the 1939 earthquake, the northern part recorded a minimal intensity. And so those places did not record a much higher intensities. But even though they did not record a higher intensity, I think by convention, even where the risk is almost zero, you still need to accommodate an acceleration value of about 1G into your design or whatever. Even where there's no, where the risk is low, at least 1G is normally recommended to be used for development in such areas. I don't know if your question has been answered.
Yes, it's been answered. Yeah, in fact, that's what I was looking at. What would be the minimum requirement, especially in designs within the northern zone? Because since most of the discussion was centered around Accra and where the FP fault is lying on. Thank you very much.
That's an international standard. Even the least prone zones, you have to consider 1G. For your design. And it was even, I think even in the 1939 earthquake, it was even recommended in it as well, the report.
Okay, thank you very much.
Hello?
All right.
Hello, Chairman.
Yes, engineer, please.
My closing remark, yes. I want to use this remark to buttress the point of the site-specific geophysical investigation. Engineer Odei, Engineer Boatin, I hope you remember our experience after the Apiati explosion. We checked over 300 buildings which look weak on the front, but then after the explosion, which simulates something like an earthquake, we realized that all the buildings, as much as weak as they look, their foundations, their structures remain intact. It is only the roofing and then the glass windows and those things that shattered. And that tells you from the geophysical investigation that Engineer Boatin and Engineer Odei did, they realized that the nature of the soil response was the one that saved those buildings from going down. And it's only the roofs and then the windows that shattered. And that is something that we need to, delve into more. It gives us why we need to do site-specific geophysical investigation when it comes to earthquake design.
Thank you very much, engineer, for your contribution. All right, moderator, we are 30 minutes past our closing time. Can you wrap up for us?
Dr. Ayers, sorry.
Yes.
Nicholas mentioned 1G. I just want to make sure that is it 0.1G or 1G?
Oh, 0.1G, sorry.
Exactly. So that's, yeah. Okay, thank you for the clarification.
Okay, I think we had a question in the chat box. He said from Samuel Asiedu, how are seismic considerations in the design and construction of buildings and infrastructure in Ghana currently being monitored and enforced? How are seismic considerations being monitored and enforced? So who will take this? Engineer Beverly or Nadmo?
I think NADMO would have to take this because this looks more like a
Master, anyhow, we don't do it. Yeah, it's just a fact. We have not. I mean, I don't think we have any mechanism of we are not doing that. It's just
No. You can't just make a blanket statement. For instance, in assemblies, we go through the AIT process. The designs are reviewed by structural engineers, geotech engineers, to look out for some of these things. So it has to do with those who do the permitting. They are the ones who are supposed to check for these things. a few assemblies is quite well developed. Most assemblies, it is not. But that is the point where the checks are supposed to be. So in principle, that is where the check is supposed to be. As to whether they do it or not.
But they were talking about monitored. Is that not the question, Jojo?
Yes.
Yes. The seismic design considerations are monitored when they are going through the permitting process. The people who review the seismic designs are supposed to look out for certain things. The people who review the UTEC reports are supposed to look out for certain things. So that's the first screen. Beyond the permitting, I don't know what goes on, but I know that where they are serious, they do some checks at that point to see if you have taken it into consideration in the designs. And like Beverly said, she's always speaking of designs because after the designs, what happens may or may not be consistent with what should happen.
Yeah. If I may also add, I don't know the monitoring which angle of the monitoring is looking at, but from Geological Survey Authority, with our new airlines or regulations that have been sent to Parliament for passing, one of the things we are recommending is that, or want to enforce is that at least high-rise buildings should have monitoring equipment installed on them. One, having such equipment installed on high-rise buildings. Now, if you consider the cost of putting up a high-rise building and just putting just the cost of putting one or two accelerometers there to be monitoring its structural health, I don't think this is a peanut compared to the cost of putting up a whole huge high-rise. So it is one of the aspects that can also contribute towards the monitoring, because one, it will be monitoring the structural health of the building, how the building will be responding to all these small events that have been occurred. Based on those, you can extrapolate to even determine if a major one or big one occurs, how those buildings will respond. And also, you have designed, so the report has come, you have designed this building to resist 0.2, 0.3, 0.4. How sometimes to whether we were able to monitor to ensure that the building was indeed developed to that level, or it's just in the geotechnical or design report is also done. So if you have such equipment also installed, in the event of a new major earthquake, you'll be able to see the input forces from the sensors installed in the ground, and then the response spectrum from those installed on the buildings. Then you can compare. You see the input force and then the response. You'll be able to come up whether the building was able to resist that value. Because if you don't know the input force, you will not be able to say, okay, my building, what excited the building was indeed 0.2 G or 0.1 G. You do not know. So you need to know what excited the building. Then you know, okay, you develop this, you design this building to resist 0.25 G. The input force is 0.2 G, but the building collapsed. Input for 0.2 G. You said you have designed for 0.25 G, but the building collapsed. And based on all these statistics, data and statistics, for rebuilding purposes, we will be having the data to guide us in our rebuilding efforts in the event of a major earthquake. So it's one of the things that we are also going to introduce in our regulations to ensure that some of the high-rise buildings or critical infrastructure have a monitoring equipment installed on them. One, for their structural health monitoring, and two, for determining whether the buildings were indeed uh, uh, were indeed able to respond to what it was designed for. And so these are my other contribution to the question that was just asked.
Thank you very much. Okay, moderator, I think we've exhausted our questions for today. Any last words
Yeah,
before
but
we close?
we should let our remaining, apart from Mr. Ogugu who has spoken there, our remaining panelists, if they have any closing remarks they want to make. If not, then so let's give them the opportunity. Madam from NADMO, do you have any closing remarks for us, please? It's not there.
Yes, I'm here. Okay, so
Okay.
I think um, um, I'm infused with Engineer Carlin's suggestion, and it will be carried on immediately, of course, together with the institute. Then also, I think currently NADMO is trying to have an earthquake contingency plan. It's at the draft stage. And so all our stakeholders would also be invited to make inputs quite soon. And finally, I'll say that yes, NADMO is poised into improving the process of earthquake preparedness by increasing the readiness of each and every Ghanaian. So I think for now, this is what I can say. Thank you.
Thank you too, Madam. Engineer Beverly, you have any closing remarks for us?
Yes, please. I want to add that whilst we are looking at all these policies and measures to ensure that our buildings are resilient in terms of earthquake, we should also start looking at existing buildings and particularly hospitals, schools, the airports, bridges, to make sure that they are also resilient, and if they are not, what retrofitting measures can be done to make them resilient. And this should be a matter of national concern because we have a lot of existing facilities that are housing very, very important functions. We have so many hospitals all over the country. We have airports. We have a lot of schools that when we have earthquake, we should be able to rely on them for safety. And so we should start looking at how to make sure that these are earthquake resistant in the event of earthquakes. And so that's my national final comments.
Thank you. Chairman Jojo, I think I'll hand over your activity back to you. My job is done. Thank you.
Thank you very much, Engineer. Good evening once again to everybody. A very big thank you today to our panelists who have shared their valuable experiences with us. In fact, we have learned a lot today looking at the future of our built environment. I think I had a few executives here that I wanted to just say one or two things. Prof. Nemo, please, are you still online?
Yes, I'm here.
1 minute. Yep.
I think we just want to thank everybody from the Ghana Geotechnical Society and then International Geosynthetic Society. I mean, thank every member. We know this Geo Group and then Structures collaboration. And we had more than 80 people joining. And I think we may have to work together to make sure that I think we come out with some of this information education which will help in advancing our profession. This is all I can say for now. Just to thank everybody for attending. Thank you.
Thank you very much. Engineer Lote, do you want to say something to your members as well? Structures Group.
Yes, thank you very much. I want to thank all those who took part in this panel discussion, especially our panelists, and encourage the others, especially the younger engineers, that they should get involved because we are all fighting for the future of our noble profession, and I want them to take part in it. Thank you.
Thank you very much, Engineer. And on behalf of the geotechnical and structural subgroups, I want to thank you all also for coming, and I pray that future programs or activities that we hold, you would participate fully. I've been your host, Dr. Felix Jojo Aye. Good evening.
Yeah, good evening.
Good
Yeah.
evening.
Good evening.
Evening.